Hello, everybody. We're going to get started here in a couple minutes. But first, I was told to entertain the crowd a little bit, so I'll start off with a joke. I am not a comedian, so I'll only subject you to one joke right now. And I will need audience participation to make this successful. So, knock, knock.
Who's there?
A performance engineer. A performance engineer will tell you you should answer the door after just one knock. That is my joke. So my name is Mike Wong. I'm an engineer in the performance and OS team here at Netflix. Tonight's topic is all about performance and the performance work that we're doing here. This is the South Bay Site Reliability Engineering Meetup, if you don't know. It's been a while since we've had one of these, and this is actually open for other companies to host as well. So if you are a company interested in the SRE field and have topics that you want to present on, feel free to contact the organizers and get another one of these set up. So tonight, all about performance. Our team here at Netflix is a team of 8 engineers. We help the other engineering teams here understand their performance issues, help them diagnose them, analyze them, optimize them, tune them, all sorts of performance buzzwords you want to throw in there, we'll take credit for that as well. Some of the stuff that we'll talk about is the work that we do across the entire Netflix ecosystem. We do work starting from the device side, whether it's streaming TVs, mobile phones, whatever it is you're streaming Netflix on, downstream over to the hundreds of microservice applications that we write, and as well as looking at the system level performance of the behavior of our applications running in the cloud. So tonight we're going to have about an hour of talks, 4 different talks given in 4 different accents. If you can identify which one of these accents are fake, I will give you bonus points. And we're going to start with Guy Cirino talking about some of the work he's doing on the client side.
Thank you very much, Mike. I like his knock-knock jokes. I don't have one of those. Welcome tonight. Thanks for driving all the way to the South Bay. And those of you who are here, thank you for coming downstairs. I appreciate that. I want to tell you a little bit that about 2 years ago, I was sitting in an auditorium very similar to this one, although it was Building A, which is on the other side of the road. And Neil Hunt, who was our head of product, he made a very big mistake. He said to us, "So does anybody have any questions?" God, yes. I've been waiting for this moment. And yeah, you. And I asked him, I said, "Neil, what do we have?" I mean, right now we're in a bunch of countries and we're about to go kind of globally. And what are we going to do about getting Netflix to work streaming all over the world? I mean, how are we going to deal with the various networks that are out there? What are we going to do about prepaid plans and all these like wireless connections and broadband that doesn't look at all like the broadband we've encountered before? And Neil, he took a little while with my question. He was very nice guy in general. And he said, well, this, that, the other thing. But what you're talking about, Guy, that's really 7 to 8 years off. You're thinking down the road, but we're not going to be able to do that anytime soon. And I said to Neil, I said, well, that's funny because I will show it to you. I will bring this to you long before it's ready. I will give this to you, and if you come to Hack Day. And the audience just kind of sat there like, whoa, did you just challenge Neil Hunt, the head of product? I said, yeah, So here we are in Kazakhstan, streaming on a 3G connection on a TV that's sitting on the back of a car in the middle of nowhere. That's me and Kazakh man, and he doesn't speak a word of English. And he says, well, he's like saying in Russian to me, he's like, this is very interesting, this Netflix, I would like to buy this. And I said, there's VPN, but it's coming. We're working on it, and it will be there soon. So I a bit concerned that he was so ready to just buy this SIM card and pop it into a TV on a car. But he did tell me that, I mean, he had shown me like his phone, and I'd seen a lot of the phones that were out there. And actually, the internet was pretty good. I mean, this was a main way of people consuming the internet out there. This was not broadband households. This did not look at all like the internet that we had dealt with previously when we were building Netflix. And as it was catching on and more people were signing up, it was getting a lot faster, which was really nice because there was a problem that it was also getting slower in that as soon as it got faster, people would sign up and go, this is amazing, I really need to get this. But then everyone would get it. And suddenly it would get very congested. And that was kind of a problem for us when we were looking at the networks that were getting more fiber and everything was getting quick. But as we were doing it, they were, more people were signing up, and then all of the links were starting to fall over, and there were issues. And I'm sure some of you tonight have actually dealt with that in a performance audience. But I told him, just like I said to Neil, I said, look, I don't want to wait. I mean, there are real engineering challenges out there. We need to know what they are, and we need to get in front of them. So it is possible, but it's also going to involve some pretty hard cuts in the app, right? So there are things which are extremely bandwidth intensive. There are things which require fast round trip time back to the servers, and those don't exist. So this was all kind of predicated on it's better to have an app that actually works than an app that has every single feature but doesn't work. So I told him, like I told a lot of the people here, we really need to know what this looks like. And we don't need to have an average of what it looks like. I don't want to know that in the average population of Netflix users, half of them are on pretty good internet and everything works fine, and the other half, that's why I have a job. So I instead said, well, let's go start picking all of this data up and let's send it back, which immediately led to two very quick conclusions. The first was that it would be fine to just kind of average that, except averaging is a little bit tricky in that you start seeing, you don't know what the distribution itself looks like. You know what the average is, and you have no idea if that average is there because you have two very bipolar things in your distribution where you have a whole bunch of, like, say, caching behavior, which is taking 0 milliseconds, and infinite behavior where things are timing out. And that doesn't really help us deal with that. But so what do you do with the massive amount of metrics? Do we just capture everything and log everything back to our servers? Well, no, that's way too much data. So we're going to start sampling. Well, we can just pick a sample and say that this is actually what it looks like for the population. But the problem is we don't know if that's what it looks like for the larger population. We don't know how good our sample is. We don't know if the sample applies to the markets that we were looking at. We don't know how good that information is going to lead us regarding the population. And so I had then seen a talk from Jim Roskind, and he had used this term of having a massive map reduce out of every single client in the world. So why not take all the clients, let them chew on the data a little bit, and send the aggregated result back up? So now we don't have to log absolutely everything, but we can see absolutely everything. And so from that, I said, all right, well, let's build a picture. Let's see what the internet looks like. We now have this model of kind of a number of metrics which might be incredibly fast. So in the particular case I was looking at, it was network flows. So I wanted to see every single network flow that was going from a device, but I can't make one network log for every network flow. I'm going to just double my traffic volume immediately. But I do have a fast metric. There's other fast metrics such as key responsiveness, frame rates. Are we dropping frames on clients? These are bad things. But I need something which works that has flat memory usage and is very quick to insert. So if I have any one of these sets of data points, I can put it into a data structure very quickly, filter out anything that's not important, send that back up to the server. So for those of you who haven't seen it, this is kind of a standard constant binned histogram. And this is actually from some field data where we're seeing a lot of behavior is working exactly as we expected it to in the lab, and our simulations are good. And then we've got all these outliers. And the outliers was exactly where Kazakh man was standing with me when we were over there. So we were looking at these histograms, and we said, well, how do we get some usable information from that? And so spoke to some of my math colleagues, and they said, well, the trick to that is you have the aggregated data, you need to calculate the inverse empirical cumulative distribution function, which is a real piece of cake. You see, you just take this equation, and actually you just use R. R is much better at this. So I don't want to figure this equation out at all. And I just pulled in the histogram tools library that Google had already built for us, and everybody else who likes open source. Took that data that was in the histogram and then popped out this IECDF. And then I can say from that, all right, where's the median? Where's the 95th percentile? Where's the 75th? Whatever. Suddenly, I noticed the problem in my old graph. I have equal information in the area of interest as I do in the area of the outliers. I don't need to know how much of an outlier they are. I need to know that they are an outlier. I mean, when the connection snaps and stops working, it's slow. It's too slow for the user, whatever it is. So I don't need as much information over there as I do over here, where I have my 50th, actually in this blue line next to the red line, which has the 95th percentile. And there's another nice solution to that. I can actually space out the histogram in a different way. This is an exponentially spaced histogram, where I'm putting a lot more information over here on the left in my area of interest, as opposed to the area over on the right, where it's slow, and I don't need to know exactly how slow. Turns out that if you watch those numbers in the top right corner, that it didn't actually change that much. I have almost exactly the same median and 95th percentile when I calculate both of these, which led to a wonderful situation that I was now in. Now we knew that we had a lot of data, and it was better than the opinions. And to give you some sense of context of when I was debating this at the time, these are actual quotes, I will protect the innocent, that I got from a number of people internally that were telling me exactly how networks worked around the world. Well, we live in a 50 millisecond world. Thank you, that's my joke. I couldn't believe when I was actually sitting in a meeting, and there's nothing 50 milliseconds about this world. Maybe around here, but that's it. Well, no one really minds looking at the spinner when you're loading the app. I mean, it's not that bad. I mean, the app loads eventually. Do you guys mind? I mind, okay? But I'm biased. I'm a performance engineer. These guys definitely mind. And, well, why should I spend any time with that instead of implementing this new cool feature that's coming along? Or, well, there's no way our client is making that many requests. It doesn't need to do all that network junk, and I said, oh, that's interesting because we measured it. But it doesn't matter because any architecture you're going to pick, it's hard. And one of the things we needed to take away from this, we needed to make it simple and cheap to experiment out in the field. And we had to get a very quick read on what we were getting. So that's why we built Daedalus. So this is actually our viewer, in addition to the client libraries that actually are collecting the raw data and kind of chomping on it out at the edge. And this views the aggregation of all of those histograms. So as all of the clients are collecting this data, in this particular case, I'm actually going to be measuring DNS. And I was kind of curious about what DNS looked like around the world. And it actually looked pretty good. Up here towards the top, this is very fast DNS requests. Down here at the bottom is stuff that's really slow. And I see a nice band here at the bottom, which is DNS timing out. That's our client giving up. And I don't know why there's anything below that, but that's a separate issue. And this is actually, and each of these vertical columns shows a different hour of the day. So I can look across in this multi-dimensional histogram. I can look across the day and see how this is changing over time on a particular network, on a particular ASN, on a particular device that's in that ASN, whatever I want to break it down. And I said, well, that's fine. It's going to be a piece of cake, except that's the US. Until I saw this. And I'm not going to tell you where this is, but it's a lot closer to Kazakhstan than my first side over here. And that scared the bejesus out of me. And that is actually what we were dealing with. So we had to be really, this immediately informed, all right, you guys got to be really serious about your DNS caching. Okay, I know you want it like really short timeout so that you can like fail over to another region. This is going to be a problem. So we started, and we've done our visual inspection. We have a general sense of what the data looks like. We know what the distribution roughly is. And now we need to start getting some hard numbers out of it. We need to say, okay, well, how is this being affected build over build? Are we getting better or worse? And what does it look like? How do we compare it across ISPs? And so, like I said before, the IECDF helps us with that, and our nice little bit of R. And that leads us to being able to visualize it. Now, in this particular case, in the graph I'm about to show you, not this graph. The 50th percentile that I've calculated from all of these histograms is here along the x-axis, and the 95th percentile is along the y-axis, so that I can get a sense of how far apart are these two things. So when I'm looking at my 50th and my 95th, if they're really close together, I have a very well-behaved network. It never fluctuates at all. And if the 50th gets really far away from the 95th, I know that I can't count on connectivity around that particular metric. So I'm going to have to use some pretty serious caching strategies. Now, of course, in some cases, it turned out that the 95th was actually faster than the 50th percentile, which was time traveling. And that was a problem that we had on a number of TV devices that happened to have not very good clocks. And so they would show us things that were kind of unbelievable. So you always have to take a look at your data. But, and then what would sort of happen here is if I was along this line, it would actually just be, the 95th was equal to the 50th. So at whatever latency it was just slow or fast, but it was consistent. As I got into this top left quadrant, very inconsistent. This is kind of the dangerous area. So we're kind of okay in this green area, but as we kind of crawl up, things get a little more challenging. So this is actually, in that same segment of networks before, that data by ASN. So this is by ISP, more or less. And the size of the bubble gives you an idea of the population size of how many TVs we have in that particular region. And these are all really good. I don't really have an issue. I mean, they're all kind of clustered really tight. And those are getting kind of slow. But even on the top right over there, it's still constant. So it's latent, but it's constant. All of the data is getting to the device. Now that ISP up there, that's what keeps me up at night. This is really our challenge when we start looking. And then I colored these based on similar network characteristics using k-means. So we got a sense of which populations we should be testing against. So just kind of blowing up this bottom left, I can see again, a bunch of the ISPs are acting really well, and then there's kind of things that are getting more challenging. So I have an area of interest now to start looking at new programmatic fixes to try to work around some of this behavior. And that was all pretty good, except these are TVs, smart TVs. Smart TVs tend to be owned by households that are doing all right. And they tend to have broadband that works. So then when I looked at the Android data, things got a lot worse. So, I mean, the scale has completely changed here. The 95th is nowhere near the 50th on any of these networks. So this meant that, I mean, these ISPs, they're going to be really challenging. So, I mean, again, there's a product need. I mean, we're going to need to identify. We don't know what the size of the total populations are there, but they're going to be significantly big. So we basically took all this data and we said, it's hard to look at the raw data, but it would be a lot easier if we actually just built something that would emulate it so that we could actually feel what it looks like. So this was actually an ASUS router that I took that I plugged in a display, and in my first iteration I was trying to emulate the Orange network, and I thought that would be pretty cool because the Orange network is actually a pretty well-behaved network. And then I ran into one of my French colleagues who told me, oh, no, Guy, this is not Orange, this is Orange. And so I fixed it. But anyway, I showed him and I said, oh, well, don't worry about it because now we have the ability to kind of emulate these networks. And that is actually what I want to leave you with. Don't guess. Just because the metric is moving really, really fast, we have options and we can actually figure this stuff out. So we'll be able to build better software if we can see that distribution. And I have all of the details of everything that I showed you, including how to do all that, up there on that blog. So thank you very much. With that, I'd like to hand it over to Mr. Martin, who's going to tell you about our other metrics.
Cool. Can you guys hear me okay? Great. Awesome. Let me just pass this line here. Hope that works. Awesome. So my name is Martin. I'm also part of the performance engineering team here at Netflix. And I'm also here to talk a little bit about client performance, in my case, Icarus. So first thing that might come to mind when I mention the name Icarus is that Greek guy that tried to fly out of Crete in a pair of wings, his dad built, dataless. But he flew a bit too close to the sun, the wings actually melted, he fell to sea and died. Likely that's not the case here. Icarus, in our case, is a real user performance monitoring solution we built here at Netflix. It helps us get more insight into the app performance, the client performance, as real users perceive it. we have just too many variables and too many unknowns to trust only on synthetic tasks being executed on labs. So we need real user data to really get insight into app performance. It really helps us understand how changes we are making to our environment, to our client apps, or to our infrastructure, to our backend services, how they actually affect real users. It's also a great tool to detect issues in case we push out a bad build that introduces some perf regression in a weird device in India. We can detect that, so we can troubleshoot and fix it. Same goes for bad issues with ISPs. An ISP in Germany having issues, we can go and reach out to them and see if we can actually help with that. So getting real user data is really important. That sounds really easy, really simple. You basically just sign up for a third-party service, right? You snap some JavaScript on a web page and problem solved. You just wait for those metrics to start flowing in. Unfortunately, that's not that easy for us. Besides of the scaling issues, we also run on all sorts of devices. It's not just web and mobile. We also run on smart TVs, a bunch of gaming consoles, your Xboxes and PlayStation, and even some weird cable TV boxes running Windows CE in Belgium. And we actually need to support that, and we care about that. So we need to find a consistent way of evaluating the performance in all those devices. Another thing, as Guy mentioned, we run everywhere. As of last year, we run everywhere with the exception of a few countries. So we have a really, really wide variety of networks we need to deal with. So we need to take that into account on our analysis. Because the same device might perform completely different depending on where you are. So what exactly are we monitoring? In the case of Icarus, we are monitoring user actions. So things the user can do in the app, like launching an app, opening it, navigating to a page, like getting details for a movie, for example, playing a title, things like that. So that's what we're trying to capture here. What are we measuring? And that's when the question starts to get really interesting. When does this timer actually start and end? And we had really, really long discussions around that. Short answer is it depends. It depends a lot. There's no standard that will define that, at least not for all the devices we have to support. So we had to create custom timers for basically each action we need to support, each user action. For example, app startup and navigate events, they will have at least 2 timers, being TTI and TTR. TTI is fairly well understood as the time from when the user initiates the action, when he clicks on a button or an icon, until that view or page is interactive. Things might not be fully rendered at that time, but the page is interactive. And then we also have, to complement that, we have TTR, or time to render, which starts exactly at the same time as TTI, but it ends when all the items above the fold, or things that are visible without scrolling, are fully rendered. So we have that timer. The other custom things, so if the user is trying to play a title, we have play delay, which is the time from clicking on play until the title actually starts playing, and we need to keep track of that, plus a bunch of other metrics. The key item on this is the timers really need to track what the user is feeling, what the user is trying to do. That's the key part of this. We need to create timers that track what the user feels. We have really, really high dimensional data. Really complex device categorization. We have thousands and thousands of combinations of devices, platforms, apps, versions, and so on and so forth. And we need to be able to split all of those. We need to take geo into consideration, regions, countries. A lot of our customers are, internal customers are part of our CDN team. So we need really granular network classifications. So your ISP or the ASN, the ISP network you're talking to, or the AWS region you're talking to, or if you're over Wi-Fi or cellular network. We run a lot of A/B tests too. So, and those A/B tests might affect how the client behaves, how the app behaves. So we need to track those too. We need to track A/B test out to see if the user is getting a different experience or not. Some actions also have different facets. So app startup, for example, you might have a cold startup or a warm startup, and we need to keep track. We need to be able to differentiate those because those are really different things. Now that you know a little bit of what we're trying to track and what we're trying to achieve, I'll go really quickly through how we actually make that happen, how we capture all this data and how we process that. So we have all our devices, all our user devices. They run our client. The client implements those timers. They capture the timers where the user tried to do something. It buffers in the client and then flushes to our data pipeline every hour or so, depending on network conditions, if things are good or not. It just flushes to our data pipeline, and that ends up in Hive, which is one of our data warehouse solutions. Even not being fast metrics, like I mentioned, the volume is fairly considerable because this is not sample data, it's everything. You want to see everything. Obviously, this creates a few challenges on how we process that, how we analyze that, and how we actually present that in a meaningful way. We try a bunch of different things. But first iteration, let's just try and plug that to Tableau. I don't know how many of you actually know Tableau, but that didn't work out well at all. We blew that thing away really quickly. Next thing, we decided let's just try Druid. Druid is really great. It's distributed. We can scale up and down. That works great. It's impossible to load all that data into Druid. So, okay, great. Let's just try to pre-aggregate, like pre-calculate a few percentiles and a few statistics, and then obviously split by all those dimensions, upload that to Druid, and then we can aggregate all of that in Druid. If you guys don't know what Druid is, imagine it as a cache in front of a Hive table, for example, where you can run functions on that cluster on top of that data, which works really great for us. Because we can actually aggregate data in Druid, and it works really well. Problem is, to present that in a meaningful way, we need to roll up those percentiles and those statistics, right? And the only way of actually getting that done in Druid itself is using weighted averages. And as you guys might imagine, using weighted averages on top of percentiles, it's not great at all. We knew that, so obviously we decided to evaluate if can we actually live with that error or not. As it turns out, the mediums are not that horrible. They were fairly okay for most use cases, but the ends, I mean, the top and bottom percentile, those are really horrible. And we couldn't really live with that at all. We needed something better because that data could lead us to some really, really bad decisions. That's when data sketches came in. I don't know how many of you are familiar with data analysis and data sketches. I don't want to get into too many details, but basically, in summary, it is a data structure that resembles some bigger data set, but it still preserves some essential features of that data set. The advantages of actually doing that and using that is because the output, the new data set, is significantly smaller. It's way, way, way smaller. And it's much faster to operate on. So it could do things in real time, which is great. There are a bunch of options you could use in cases like ours. Like Yahoo has sketches, and there's a ton of those. But we opted to use tdigest as our data structure for sketches. I will not get into details of tdigest. You can get more details on GitHub, on Ted Dunning's page there. But it's a really great sketch if you're working with rank-based statistics, including quantiles. It works really well in parallel systems because you can create all of those small sketches, and all of those sketches are really easily mergeable. You can merge them really easily and then extract the quantiles out of that. Extremely fast, and like judging by our tests, it's really, really accurate, a lot more accurate than their weighted averages. So we decided to go with that. Great. So we process all those small sketches with Spark jobs. We upload those to load them on Druid, and then we build the module internally here to go and merge those small sketches and basically give us our quantiles and a few other statistics we care about. Great, excellent. That gives us querying capabilities, but performance engineering team, we're not the only consumer of this data. we also need to present it in a nice way for other people. We have our client teams, the teams actually developing the client apps. We have our CDM team that actually consumes that data, plus a bunch of other teams. And they, well, tend to prefer a UI to go and query that data. It also needs to be flexible to actually accommodate all the needs from all those teams. So we decided to build a custom React and Node.js application, still developing heavily on that and improving every day. And now I'll go quickly through a few use cases of that app we built. A very, very common use case for us is comparisons. People like to compare things, compare different items in the same dimension. Obviously, different teams, they would care about different dimensions. Teams developing an app would care more about platform categorization dimensions, for example. Teams working with networks would care more about the network dimensions. So the UI needs to be super flexible. It actually allows you to filter and group by any of the dimensions I mentioned previously. So it's really, really flexible. And in this case here, I'm pretty sure I have only iOS selected as a platform. I'm only plotting mediums. I only have one action, which is cold app startup TTRs and time to render. I only have a few countries selected: Brazil, India, Mexico, and United States. And I'm breaking by country. I'm comparing countries. A simple time-based chart. You have on the x-axis, you have your times, and the y-axis, you have the timer durations. As you can see, what looks pretty interesting to me, at least, is that Brazil, for that app TTR app startup, is taking longer than India, which is not something I would normally expect because, well, India is a lot far away. Then we can do something interesting. We can add an extra filter option. We can lock to a single device, in this case, iPhone 6s. Great. That changed quite a bit. You can see that India now is taking a lot longer than Brazil, this example. That's because we have bias in the data. And we need to be aware of that. Everyone analyzing the data needs to be aware of that. So we like to always stress that to use. It doesn't just pay off to have all this data available if you don't really know how to analyze it and actually read it. So we like to always emphasize that. Different visualizations. We're trying obviously different visualizations. In this case, you have a CDF or a cumulative distribution function, where in the x-axis this time you have the transaction duration there, and on the y-axis you have the percentage of all those transactions that completed in less time than that. So different way of visualizing sort of the same data. This time obviously we're breaking by iOS UI version, and as you can see, even with a locked device, you can see there are clear differences between the same app running on the same device, just different iOS versions, which is fairly interesting for us at least. We can also analyze different facets of the same metrics, like app startup, where I have cold and warm. In this case, we have warm startup rate on PlayStations and iPhones, so we can break by that too. A/B test, as I mentioned before, and that turned out to be a fairly popular feature. Same graph as before, same CDF, but in this case, we're comparing test cells, so different experiences the user is getting in the same test. So same amount of users allocated to that test in each cell, and we're comparing that one specific metric. In this case is details page, the time to load the details page, and this was a specific test to prefetch, different ways of prefetching data for a details page, if I'm not mistaken. As you can clearly see, it's fairly different. You can clearly see that usually cell 1 for us is our control, and the other ones are different experiments. So you can clearly see that at least cell 5, it's loading quite faster. So it's tend to be really nice. We're starting to dribble into anomaly detection too. That's why, because we have so many dimensions, it's really, really hard to keep manually analyzing those things and finding weird behavior. We're still trying new algorithms. This, as I mentioned, is fairly new. In this case, I think is ESD, so the extreme studentized deviate. But in a nutshell, it runs this anomaly detection algorithm over a time series. And we try to do that with all possible combinations of dimensions. And based on those results, it actually alerts us in case something looks weird, so we can go and analyze and try to understand why that happened. We also work here on a feedback loop, so we can improve things over time, improve the detection over time. Going forward on Icarus, we adding more and more metrics, namely resource utilization metrics, CPU utilization, memory pressure, and so on and so forth on devices. We're looking to add device profiling. We're instrumenting client code right now to get some profiling into clients to see in case something regresses, we at least know where to look at. So that tends to be really, really good for us during the troubleshooting process. We're exploring different visualizations. I'm really a big fan of the frequency heat maps guy showed before. They're especially powerful for weird distributions, so I really like those, and we can get those out of T-Digest too. So we're looking to get that in pretty soon. And I'm also studying and trying to better understand the connection between this perceived performance on the client side, user acquisition, and retention. But that's all I had, and with that, I'll leave you with Vadim, which will talk about auto-scaling.
Hello. Thank you, Martin. Thank you, Guy. So we heard a lot about clients and about various challenges in the client space. It probably comes as no surprise that those clients talk to servers, and Netflix operate pretty massive infrastructure on the server side. To give you some idea of our scale, we operate about 150 instances. Instances refer to AWS VMs. 150 instances at peak globally. We're in multiple regions. About a third of this footprint is our data tier. We cannot auto-scale that. About 2/3 are stateless or supposedly stateless services that could be auto-scaled, and we do scale them. So we realize roughly 30% savings from auto-scaling, which translates in about 30,000 instances, right there. So you might think, well, 30,000 instances is not a lot, but it actually, we can make a good use of it. So why do we scale? One reason is more on the philosophical side, is the data center versus AWS cloud or whatever cloud provider you're in. Cloud supposed to be elastic, take only what you need, don't take more, there's no budgets, there is no, if you don't use it, you lose it, kind of data center mentality, and we wanted to encourage our service teams, our developers, to follow this paradigm. And there is another reason, very pragmatical reason. Well, there is a lot of cash here. We can save money, very real money, actually. Netflix use reserved instances. We pre-purchase capacity. AWS allows you to do this. So the money, we have the capacity. But we can repurpose unused capacity, those 30K instances, for a lot of things. Encoding is one of the most obvious use of that unused capacity or saved capacity. We can run encoding in small chunks during off-peak hours, during our trough hours. We can do this over a period of a few days. Usually there is a pipeline, there's a schedule of encoding. So we don't have to have any extra capacity. By the way, a couple of years ago, or a year and a half, our encoding team published a blog about it. I encourage you to read it. It's a very interesting blog. Pre-compute. We spend a lot of time and compute resources generating recommendations. That's a Netflix secret sauce. So we take it very seriously. And we found a way of running pre-compute, again, during night hours, when we can realize gains from that unused capacity. Failover and red black are a little bit more involved concepts. Auto-scaling allows us to fail over more efficiently. We do not have to provision a lot of capacity. we do not have to provision the full capacity in every region for failover. And red blacks, if we push early in the morning when our server groups are not at their peak size, we can save on failover, on red black as well. Last point, the one before last, curing cancer, our very own guy Cirino, last year, a few months ago actually, right? Yeah, there was a hack day project. We used our trough capacity to join Cure in the Box. It was a hack day project. It was successful. Guy says yes. Right, unfortunately. Guy can tell you cancer in Russian, by the way. Ask him. Should you auto-scale? Well, my answer is yes, you should. And you can get the same benefits that we get. If you're running in, say, Google Cloud, or if you're running on demand in AWS, that auto-scaling translates into dollars. It's money. It's money on the table. If you're using pre-purchased capacity, then you can repurpose this capacity for something else, something useful, just as we did. And there is a word of caution. So auto-scaling is something that you can apply for each server group or ASG individually. And there is certain things that you should be aware of before you just start auto-scaling everything. All kinds of irregularities in traffic, bursty, sticky, uneven distribution of traffic across zones or individual instances, they usually do not play so well with auto-scaling. You can probably work around it, but that's not, I guess, the normal use case. Small ASG sizes, we found that it's not worth bothering scaling those because each scale event, if you're less than 10, each scale event is more than 10% of your capacity each way. It becomes a little bit too bumpy. Next question, true or false? Auto-scaling impacts availability. False. If done correctly, it does not. At least we didn't see any indication that it does. What does impact availability, however, is under provisioning. So if you run your auto-scaling groups under provisioned, there is a very good chance you will run into trouble. So I want to separate these two concerns. One concern is knowing your performance characteristics, is knowing the current capacity of an individual instance. It's knowing the sweet performance band where you can operate your servers. Regardless of whether you scale or not, you have to know it. Once you know it, you can use auto-scaling to operate them in this band all the time. And I'll show you examples. A little bit, this slide is AWS specific. When people think about auto-scaling, it's kind of like a black box. I wanted to show you what's inside that black box a little bit. There is two moving parts. One is CloudWatch, and another is the scaling group itself. So scaling CloudWatch alarm operates on a metric. It's actually aggregated metric. And you set the threshold, you set the number of evaluation periods that your metric have to exceed the threshold, then your ASG gets notification, then it executes the scaling action up or down, and you have to specify the amount of scaling and the cooldown or warm-up time. As you can see, there is a few, well, here there is at least 5 tunables. You have to pick them, you have to tune them, you have to monitor them. We'll see how it plays out later. And I'll also show you some examples of misconfiguration. What metric to scale on? That is the question. And actually, a lot of people, I worked with a lot of teams who ask the same question. It's more of, it basically comes down to the question, how do you measure your work? Some people measure work in distance traveled or the weight lifted or the number of widgets produced, while others tend to think about it in terms of how tired they are. So there is fundamentally 2 different ways of measuring your work. Throughput is a direct measure of your work. Measure how requests you processed, how many messages you got from SQS, something along those lines. Resource utilization is a measure, think of it as how tired you are. You can measure both, you can scale on both. There is, as usual, there is pros and cons. My personal preference is to scale on throughput because it's a very direct metric. At any given time, you can, once you know your band, your throughput per instance, you can very easily determine how many instances you need to accommodate incoming requests. The cons is that it tends to drift over time and it prompts to changes in your request mix. ASGs can process different kinds of requests, the same ASG. So that mix tends to drift over time and maybe during different hour of the day. So that affects scaling. Utilization metric is pretty simple. You set your target, you try to keep it on target, say CPU utilization at 50%, keep me there. What we noticed though, utilization metrics tend to be more jittery and more noisy. And also it's harder to reason about those metrics. Autoscaling on multiple metrics is what a lot of teams tried doing. It can be done. There is certain disadvantages of it, or it could result in unpredictable scaling behavior. It's harder to reason about what would happen and how those different metrics would interplay with each other. You might get contradictory signals from different metrics. Your ASG start oscillating. Here at Netflix, we recommend the setup where you have a single scale-up policy on throughput, scale-down policy on throughput, and emergency scale-up on CPU. We call it the hammer rule. So if something happens, you get a spike of traffic, at least we scale you up quick on CPU. Okay, my favorite part, examples. So here we see a graph that represents the total volume of requests that we process versus the cluster size. This is our more or less standard pattern of traffic. This is real data, by the way, from one of our ASGs. So now you can see that our cluster size goes from maybe 50 to 350. That's 7x spread. That's pretty good. Wish they all scaled like this. You can also see that the shape of the cluster size line, the red line, it kind of matches the blue line, the blue area, which is also good. But this graph doesn't tell the whole story. It doesn't tell you what exactly we scale on. Here. Now, these graphs are aligned in time, and the bottom graph represents our throughput per instance, and that is exactly the metric we scale on. We set the band. This is scale up, 110. Scale down, 90. We want to keep our throughput per instance in this band. Now see what happens. When our throughput is within the band, ASG size is flat. It's not scaling. As soon as we start bumping against the ceiling, it starts scaling up. The throughput goes down because we scale up, the throughput per instance. So we keep bumping against the ceiling through our peak, and then we start scaling down, and then we bump against the floor, and then we scale up, and that repeats. So this is the normal pattern of scaling. And next, we'll look at some examples of misconfigured scaling. No rush scaling. Okay. So from the top graph, you see right away that, well, the traffic, there is very significant peaks and troughs in the traffic. It's about 3x, right? But ASG doesn't scale. It doesn't follow that pattern. It stays between 300 and 400 instances. Also, if you look at throughput per instance, we cannot keep it within the band. It goes above. This is dangerous zone, by the way. So this is when you say, oh, autoscaling can affect my availability. Misconfigured autoscaling can affect your availability because you're consistently above your threshold. Well, and here, if you're below, capacity wasted. So, well, the problem here is that the scaling amount is too small. If we increase scaling amount, the cluster size would follow our traffic more closely. Next, twitchy scaling, twitchy. So this is somewhat the opposite problem. Here, and actually, I spoke with the person who set it up, and he said, oh yeah, I was a little bit worried that we don't get enough capacity, so as soon as I reach my upper threshold, I'll just double up in size, no problem. So, well, kinda, sorta, it's no problem, it's fine. We're below our threshold, but what happens is we double up, and then the scale down policy kicks in, and it scales you down, and then within the band, we're not scaling, and it repeats, and it goes like this. So this is not necessarily a threat to your availability, but this is something that you should be aware of, because again, it's a waste of capacity, and it's just a capacity churn. Okay. Notice yellow and green lines, they are the same. By mistake, we configured our scale up and scale down thresholds to be the same. So ASG is confused, really. As soon as you scale up, you're crossing my scale down threshold, so I need to scale down. As soon as you scale down, well, the scale up threshold is crossed, so I need to scale up, and it keeps oscillating. So the only thing I guess that saves us here is that we scale up by 10% and scale down by 5%. That's why we're kind of following the traffic pattern. But this is bad. This is this constant churn of capacity. Okay. And this is the last slide. AWS released target tracking. No more of this no more of this setting up individual policies, scale up, scale down threshold. You can think of target tracking as a thermostat. You set the temperature, it keeps the temperature. Pick a metric, set a target value, warm-up time, you're all set. Here's an example. Regular AWS scaling policies, step scaling policies, target tracking. As you can see, it's much, much smoother. It's also easier to set up. It's also supported by Spinnaker, our development tool. This is the way to go. Thank you, guys. To you, Brandon.
Activity. G'day, my name is Brendan, and I'd like you to imagine that you have a server that's running at 90% CPU utilization. What would you do as a performance engineer given this server that looks like it's CPU bound? What are the next steps for analysis? Does someone want to try? Imagine this is a job interview question at Netflix for the job, the senior performance engineer job that we just posted. Yes? Look at the queue length. Where's it spending its time? What tool would I use for that? What tool would I use for spending its time? Which one? Sorry, the VMstat. You can VMstat's very high level. Use the system breakdowns. I can look at the queue length to see how badly we're saturated. Flame graphs are pretty good. I mean, flame graphs are pretty good. So flame graphs will show you whereabouts in your code that you're spending time, and what might be some of the rectifying. So now we've talked about some of the tools to analyze this. What would be some of the rectifying actions to make this server perform better? Kill -9, kill the application, eliminate unnecessary work. Now think about it, you've run a flame graph, you've got some time in a particular piece of code, or you've got saturation on the CPUs because the queue lengths are high. What are some of the rectifying actions we take for CPU utilization? Refactor the code. I mean, change the code, take out the unnecessary work. What about hardware changes? Add more capacity, that's going to work as well. Bigger instances, faster CPUs. So that's basics, and I do go through this in job interviews. However, and I don't like to do trick questions in job interviews, in reality, this does get pretty tricky. So this is modeled on what our production servers typically look like, and that is where we spend about 20% of time is making forward progress on instructions, and about 70% of the time is waiting, stalled at the CPU level. So for some definitions, busy is, in this case, is when the CPU itself is making forward progress, whereas 90% busy is for the first graph I drew, is an operating system metric. So that's what you typically measure. That's what a lot of your tools will show. But at the CPU level, it can either be making forward progress on instructions, or the CPU itself can be stalled because it's waiting for an external resource. That's often waiting on memory I/O, waiting on a bus, or something else. We might be doing thermal trips, and it's doing thermal cycles. Given this, there's a whole different type of rectifying actions that we need to take to make performance better, to attack the 70% of time we've got installed. Instead of focusing on the 20% of time, eliminating unnecessary work on making or buying faster CPUs or scaling up. If we buy faster CPUs, what ends up happening is we stall faster. And so you make the busy component a little bit better, but then you're just able to stall more quickly on main memory. So this is a big problem, and it's also a big opportunity for us to be able to understand this. And it's so fundamental to what we do as well. So Vadim talked about scaling up and how much effort and work we've gone into to make sure that our scaling policies track the target closely. The target that we often set is based on CPU utilization. And so this is a very important metric for us to understand properly. Fortunately, there are tools. Has anyone done PMC analysis before? Great, so we've got at least a dozen people. On Linux, there's perfstat. And if you run it in the cloud, unfortunately, you get this, not supported. So last time I talked about PMCs, I gave a talk with Jim Marrow when we were working at Sun Microsystems. Since then, I've not done much PMCs because of the cloud. And the cloud, I've been working on the cloud blocks PMC access from guests. PMCs are performance monitoring counters. They're this low-level counter that the CPU, you can access on the CPU by doing some MSR instructions and doing RDPMC, but they will cause a trap into the hypervisor. The hypervisor can then gate it and decide whether the guest can do it or not. And the way these are set up on all clouds is the hypervisor will disallow PMCs. I really wanted PMCs. So I started looking at the Zen source code to see how possible it was. And fortunately, Zen already supports PMCs. In fact, many hypervisors already support PMCs. But they're not turned on in the cloud. And the reason it's hard to know, it may be security. I mean, it depends on the cloud provider. And if you go to a cloud provider and you say, why aren't you turning this on? May it be security vulnerabilities? Suddenly, cloud providers can be very protective about it because they're sensitive and they want to look after their other customers. They don't want to say, yes, there's this huge vulnerability. It's no, we just won't turn it on. It's for security, end of discussion. So I really wanted to turn this on, and on the assumption that it may be security related, I did some research into PMCs and security and found that there have been vulnerabilities. Except these vulnerabilities are very unlikely to happen. You need to be able to run perfstat directly on a binary, and then, I mean, if you can run the binary itself, you can just run it through a debugger. If you run it directly on a binary and then you're pulling out cache information, there's various attacks you can do. Very, very unlikely. But if you think about it, if security is the concern, then instead of enabling all the PMCs, and there are thousands of PMCs, let's just enable enough to get our jobs done as performance engineers. And I modified Zen to expose just enough PMCs and had that change upstreamed. and Amazon have recently, this year, deployed it. And now you can run perfstat on dedicated instances, and it looks like this. So we get to see cycles, instructions, branches, branch misses, and some other counters, which is great. It's fantastic. And so for the first time, I get to see instructions per cycle, which is a key metric for understanding what the CPUs are doing. Now, of course, Amazon are very protective about how they did this, and I don't know if they used my code or they completely rewrote it, but I'm just happy that it's now there. So now I get to talk about PMCs again, because they are very useful, and as we know, we're spending a lot of our time stalled on main memory. Instructions per cycle, how to interpret this. Now, I've highlighted it because it's probably the #1 metric, just like a load average or a percent CPU is the #1 metric for understanding a server. The #1 metric for understanding low-level performance is IPC. IPC is how many instructions are retired or completed for each CPU cycle. Now, 0.82 sounds like a pretty good number. Sounds like light speed would be 1.0, but as it turns out, processors for a long time have employed a superscalar architecture where within the processor, it has multiple functional units that can do instruction, fetch, ALU in parallel. And when an instruction comes in, it will be broken up into micro-ops. Those micro-ops can be executed out of order. And at the end of all of this, with every CPU cycle, the processor can retire multiple instructions. Modern CPUs at the moment can do 4 instructions with each cycle. That's maximum, that's light speed. And so they call them 4-wide CPUs. So the maximum speed of the CPU is actually 4.0 for instructions per cycle. And this is doing 0.82. So there's a lot of room for improvement. You won't get to 4.0. You will if you run a NOP loop, if you run the no-op instruction in a tight loop. For a production workload, I would expect it to get to at least 1.0, and with some tuning to get to 1.5. Now for Netflix, that's huge because that will give us a very significant win for many of our instances to be able to go there. Another way to describe instructions per cycle is it is like miles per gallon for the car. The resource that we're spending, the resource you're spending on a car is gallons, and you're getting out of it miles. And here the resource you're spending is cycles, and you're getting out of it instructions. And so you always want the best miles per gallon for your car, and you want the best IPC for your CPUs. How to interpret IPC. Now again, this is based on a 4-wide CPU. So at some point, CPUs are going to go to 5-wide and then 6-wide. And so you're going to have to adjust this point as that changes. In fact, since things do change, one thing I recommend to people is if you can write an application that you know is CPU bound and write an application that you know is memory bound, then measure IPC for your known applications. And so you can figure out your own ballpark figure of what's good and what's bad, what's memory bound, what's CPU bound for your runtime in your language. So IPC less than 1.0 for a 4-wide, you're likely memory stalled, like we are for many of our instances in Netflix Cloud. Given that you know that, you can fix it by changing the data usage and layout to improve CPU caching and memory locality. There's this whole science, especially in Java performance tuning, of doing data locality, including things like using an array instead of using a hash map. But it's a lot of engineering work if you want to go and change your code, and it really helps to be able to measure it first so you know that that's going to pay off. Otherwise, you're shooting in the dark. You can also choose larger CPU caches by making a hardware decision. You can have faster memory buses and interconnects as well to improve that performance. If your IPC is more than 1.0, so you're at 1.5 or 2.0, you're likely instruction bound. And so now it's about eliminating the instructions, finding out what they are, doing a flame graph, doing a profile, and finding areas to eliminate unnecessary work. Hardware changes you can make include scaling up the CPU, finding faster CPUs, and also scaling up the microservice as we use at Netflix. So this is just an introduction. This is like the first stopping point when you get into PMCs, IPC. What's the IPC for my instance? And then when you figure that out, there's a lot more PMCs to drill down further. The architectural PMCs that we enabled in Amazon EC2, now these are only for full dedicated instances, so you need like a M4.16XL. These are special because Intel have put these in the CPU ID instruction, in the CPU ID binary interface. So when you call CPU ID, you can find out various information about the processor, including which of the architectural PMCs are enabled, which is pretty crazy because there's a lot of PMCs. There's hundreds and hundreds of PMCs. But they've picked these as the top crucial 7 to measure. You have unhalted core cycles, instructions retired, unhalted reference cycles. These can be helpful so you can determine how much you're turbo boosting. Using the instructions versus cycles gives you IPC. We have last level cache references and misses. A last level cache is the largest cache, hardware cache. And then you've got branch, instruction, retired, and branch misses. This is pretty good because it gives you a lot more information about where to tune on the CPU. Tools need to make use of this. So I've got a very quick tool that I wrote called PMC Arch, which just does all I can with those 7 architectural PMCs in counting mode. And that's where I'm counting them per second. They can be used in different ways. You can use them in sampling mode and get stack back traces and program counters out as well. So I put this on GitHub. It's a very simple shell script, but I'm printing out columns for each of the 7 counters and doing things like here's the IPC, here is the branch prediction miss rate, and here is the last level cache hit ratio. So really useful. There's not that many other tools that use PMCs yet. An example of one that has done a lot with PMCs is Intel vTune. But of course, you couldn't run Intel vTune on the cloud until now. At least now you get 7 PMCs. But one I wanted to mention is TipTop. TipTop is a version of Top that gives you a column for IPC and some other PMCs, which is pretty good. So it's showing you the instructions per cycle for each process. At Netflix, I'm already using these to analyze what's going on and get the feel for the cloud and where our bottlenecks are, and we're going to look at monitoring them 24/7. Facebook already monitors the architectural PMCs 24/7. Google, I know at least use IPC, or sometimes it's referred to as the invert CPI, cycles per instruction. Google had an interesting paper, CPI squared, where they're using CPI to find out which instances, when you put a new workload on an instance that interferes with the caches, maybe you should move it somewhere else. It's a fairly interesting use of this high-level metric. It's going to get more important in the future. So back in time, processor vendors were scaling CPUs by making them faster, and there was the CPU DRAM gap. And that's where CPUs were outstripping the speed of main memory. That stopped in around the year 2005 with 3 gigahertz processors. Nowadays, processor vendors are scaling up by adding more cores and more hyperthreads, and also multi-socket configurations. These all put more pressure on the memory buses, and the speed of the memory buses and the size of the caches are not increasing at the rate that the CPUs are scaling. And so we still have this gap, and this is why this type of analysis is so important. Thank you.
Thank you, Brendan. So we're going to start setting up for a short 10-minute Q&A. While we're doing that, we got a couple of goodies to give away. The first one is we have this beautiful chaos engineering book written by our chaos engineering team here at Netflix. Not only is it written by them, but it is also signed by them. So the lucky winner of this book, randomly drawn, Trevor Roberts. Is Trevor still here with us? All right.
All right. chaos engineer.
Congratulations. We have one more goodie to give away. Oh, up here. It is a crown hoodie, a beautiful crown hoodie to keep you warm in these frigid summers in California. The lucky winner of the crown hoodie is Julia Yang.
Hope you like the crown. Yeah, just turn it on. Oh, it's on.
So we'll take Q&A now. We have this lovely box that we'll throw around, and that acts as a microphone.
So speak into the top part here.
Right there.
Ready?
Oh,
No, I'm a skier.
you're wise.
So I have a question to Brendan related to the interpretation of CPI. The question is, the examples that you presented, the analysis that you presented, is that for compiled code or for interpreted code?
This is JIT compiled code. And so the examples that most of the time we're running Java, but we have some microservices that are Node.js. Both of them are JIT compiled.
Okay, so basically that reflects the quality of the JIT compiler more than it reflects the nature of the code.
Yes and no. So it's interesting because I have worked with the Java C2 compiler to improve IPC. And you can do things like change how much inlining it does. Because if Java's very, very, very aggressive with inlining, it'll inline up to 9 levels deep. And what that ends up doing, I was having problems where some applications would have 1 gigabyte of instruction text that the Java C2 compiler had omitted. That's a phenomenal amount of software. It's like it breaks my head. So because Java will inline so many levels down, and so you can relax that and say, don't be so aggressive. And so the result that Java has compiled it down to, I got it down to 100 megs of text instead of a gigabyte. That's going to cache a lot better in, say, the instruction cache and the LLC cache. The problem is I really need to get it down to 20 megabytes for it to really be hot out of the caches, and I haven't got it down that far yet. And so part of the problem is not so much the compilers, but we have so much code. And so supporting so many different devices, we have a fairly massive code base that Java has to execute. And so that's why.
We need different strategies.
Sure.
In front.
Question for Vadim. So you talked about load balancing policies that are kind of flat. They have like one adjustment rule. If you cross high water mark, pull it down, cross low water mark, pull it up. But when control theory people do this kind of thing, they have two rules. They have a differential equation that goes fast and a differential equation that goes slow, like in Kalman filter. So that gives the strategy some stability that you were seeking, but you were writing a very flat strategy. So it might be useful to look at Kalman filters and to write two differential equations, not one. I don't know if you have tried that.
Mike.
We have not tried that. Thanks for the suggestion. I'll probably talk to you offline about that. So we have some internal tools that assist with scaling. We rely on AWS, and we prefer to rely on the tools that they provide. They simply do not have this implemented. So target tracking is, again, something that we see a lot of good results with, and we're moving towards that direction. But we would rather rely on something that AWS gives us out of the box. With that being said, I'm personally always interested in new ideas and methodologies around it. So thanks for the suggestion. I'll chat with you.
Well, if we have some AWS people here tonight.
No pressure.
No pressure, but differential equations. Thanks, guys.
Yeah, hello. I'm Michael from Caldera. I have a question about the analytic system you just mentioned, about the Druid and data sketch. I remember there was a Netflix open source system called Atlas about doing similar things. Is it the new system going to replace Atlas, or it's used together?
No, those are completely different things. We use Atlas mostly for backend systems, and this is purely client side. So it's definitely not replacing Atlas at all. Atlas has different uses. This is just a way for us to ingest data coming from clients from real user devices. So it's not replacing Atlas.
But why you build two systems? What's the difference about client metrics and the backend metrics?
Technically, it was easier for us to actually work with that because all those events were coming through our data pipeline. They were arriving in Hive already. So it was much easier for us to work with them that way and load them that way than actually loading them, aggregating them, sending them to Atlas. And then we run into basically the same issue we were running before. So.
Thank you.
All right. Hi, my question goes to Brandon. I have very special interest in your talking about the performance counter because I used to work for Intel. I've been spending 10 years on performance counters because I'm doing compilers. I constantly use that.
Hooray, there's another one of us, another PMC nerd. Yay.
Yeah, we're going to talk later. Well, my question is when you're talking about the JIT code, not the native code, and if your data, your performance counter shows there's a huge memory, huge cache loss, cache misses. How could you do that with the Java code? Because for native codes, you could do a bunch of things with data locality optimization, like inline, outline, the data members of huge structures to put in the code session or hot session or read, get a layout to the ELF, the ELF link mode. We could do other things with native code. How could you do with the Java JIT code, because Java don't have the Java standard don't have the definition of the data layout. Because you could do a bunch of things, totally different in Java. So how could you do that? Because suppose you have no access to JVM.
Right.
Of course you can modify that. It's open source, but suppose you don't have it. How could you do that? How could you optimize with the data locality?
So I'll answer briefly, and I might get Vadim to help. But you're right in that when you have more control over, if you're writing in C, you've got so much more control over things, and when you're doing hash locks and whatever, you know exactly what's going on. With Java, you're removed. However, there are some high-level data structures that do make a difference, like hash maps versus arrays. And there is a bunch of documentation on layouts within Java of objects. Actually, one thing you can do is like reducing your object allocation and trying to do zero copy. I know you're one step removed, but trying to do zero copy so that when you get data, you're able to process it and finish it without putting it through a number of new objects. So I think it's like being aware of memory usage. You have more data locality.
So, well, in Java, certainly it's harder to control because in Java we used to pulling in a whole bunch of libraries and we have very little knowledge or control over what those libraries are doing in the background and what they're allocating and what kind of nasty things they might cause. And we've seen that happening. But there is a few very distinct patterns or anti-patterns, if you will. For example, all Java developers love hash maps, and they're great. I love hash maps. I love them too. Well, except when you don't need random access, you usually do not need a hash map, and you can do with array.
Too much love.
And a lot of time, what we've seen happening is people don't even realize the data sets are sorted, and they can do without hash maps. So there is a lot of things. That's why the work that Brandon does helps us get visibility into that and find those patterns and address them. You're right in the sense that maybe in Java it's somewhat limited, but we do have still a lot of wiggle room.
Oh, and there's direct byte buffers, so if you really want to get crazy.
A bit extreme, but.
And so more things have moved to the compiler, as Dan was pointing out. So there are some things we can do. There's a lot of tunables for the JVM compiler, which I've been playing with for tuning PMC performance. So.
Take one more question if there's one. In the back.
Actually, let's do two. We'll do this one and that one. Ready? Hello. Yep. Oh, it's kind of like a follow-up on the last question. So in Java, when you have like bad IPC, it's usually due to certain patterns, certain code paths. So it doesn't happen like for the whole second, right? It happens when you execute this function and it sucks.
Yep.
How can you tell it?
So I should say we've only had PMC access now for like 6 weeks or so, or 8 weeks. So it's really, really new in the cloud. It's only for the large dedicated instances. And so that's the next thing to work on. There is a way with PMCs to do what's called sampling mode. Actually, there's a number of approaches, but one of them is sampling mode, where PMC will do an interrupt when you've done 10,000 LLC misses. You do have to worry about skid and things like that when you use sampling mode, but there is an approach for that. Hopefully, we'll have some nice blog posts that get into that topic. Actually, if you use a profiler like Intel vTune, then they already will have a column for IPC next to the function names. Yeah. Yeah, vTune supports JIT. We use perfmap agent on Java, so we can dump a simple file and use our own profilers with it. So.
Or you can rewrite it in Rust.
So I had a question for Vlad, and thank you all very much for speaking. I always love the variety of topics we have, but specifically you talked about the model of an application for scaling it up and down. Is that based on observed characteristics? Is that a synthetic model? Can you talk about more how you develop that so that way you know that if it's growing this fast, you might be in trouble?
Right. So essentially, you're basically asking, how do we come up with those bands? How do we come up with those thresholds? Right?
Yeah, how do you know how the application behaves other than observing it?
Right. So there's a few things that we do. First of all, we call it squeeze testing. It's more along the lines of load testing. Load testing, I think everybody's familiar with that. You have some kind of synthetic workload that you run against your instance and see how they perform, and sometimes, more importantly, how they fail. Because it's very important to know if you have a gradual, a slow burn kind of degradation in performance, or you have a hockey stick when all of a sudden it just falls off the rails completely. So, and we do testing to determine those limits. We also have internal tools, since all mid-tier services at Netflix use our own IPC library, and we control the traffic. We also use tools for squeeze testing with real production traffic. We can allocate an ASG with a single instance and divert a portion of traffic to that ASG. And it's practical experimentation. That's how we determine those. That's how we determine those thresholds.
That's test in production.
Yes, with test in production. So, but that I think the important part is that allows us to not make guesses about our workload, and that allows us to use our real production workload mix. So we try to be as close to production as possible. And also with target tracking, I'm personally really happy that target tracking is there and we can use it, because we don't have to worry about the bands, and it takes a lot of guesswork out of it. So the only thing I have to worry about is my kind of like a single threshold, upper threshold, more like. And also, well, you have to keep in mind that there are certain situations that autoscale simply cannot catch. If your traffic doubled up within a minute,
like
no.
Releasing House of Cards, really.
Well, that's a slightly different story.
Yeah, you're going to get DDoSed.
Well, that's all the time we have for Q&A tonight. We'll be hanging around if you guys will be around for beer. We'll be around if anyone else wants to ask us any questions. Before you go, our esteemed manager, Ed Hunter, has a few words.
So first of all, thank you everyone for coming to our first meetup with me as the manager. This is great. Hopefully we'll get a chance to talk to all of you at some point in time. I want to say that most of the performance team is actually sitting on the stage here, and Emmer over there. So if you're interested in performance, come chat with us about that. My boss Coburn's back there, so be sure to tell him what a good job I did. There are a bunch of other people from Netflix. Lauren from Talent is back there, so if you're interested in learning more about the culture and about Netflix, go chat with her. Anyone from Netflix, put your hands up so that we know. So we have people from security, from Insight, from all different engineering groups. So if you want to find out other things that we're doing, certainly go and find those people, seek them out. And the last thing I'd say is one of the reasons that we do these things is for people to increase the size of their networks. So go meet other people you don't know and make connections, and you never know where that might lead. All right. Also, we have dessert.
Oh, nice.
Beer dessert. Beer dessert?
No,
Oh.
regular dessert. So go enjoy dessert. We have another hour or so to kind of meet and greet. And thank you once again for coming. We'll have another one of these things probably another quarter or two with hopefully another set of really interesting talks about what we're doing. Okay.